Okay, so now that we have the basic priority queue, we've talked about how it works, here's the pseudocode. All right, so define your function on the graph, or define it as a method on the weighted graph class. Just call it shortest path or Dijkstra's or whatever works for you. It should accept a starting vertex and an ending vertex. Are we going from A to E, from A to Z? Are we going from SFO to LAX? Whatever the vertex names are, it accepts two, start and end. Whichever one comes first will be start in our case. Then we need to make a couple of data structures, and we'll create our object. We can call it distances. This will act as this table here, where for each vertex, we're going to store the current shortest distance from whatever start point. It doesn't have to be A, of course, but let's say we're working with A to E again. We're going to store in this object the shortest distance from A to B, from A to C, A to D. And at the very beginning, we initialize everything to infinity, if you remember that, because we don't know how far it is from A to C or A to D. The only value we know for sure is A to A, which we start at 0. Then after initializing the values in the distances object, we're also going to make our priority queue. So we make a new priority queue, and it starts out empty, and we add each one of our vertices into that priority queue where we set the priority to be the distance from A. So basically, we add all of the vertices in with a priority of infinity, except for A with a priority of 0. So of course, we get A first. But then later on, we'll have actual values in there that aren't infinity. And every time we dequeue, we get the smallest value back. And that's where we begin. That's what we visit first. Okay, so this just initializes things. And there's actually one more step. We also have to create our previous object, where it's just a simple object where we have a key for every vertex, and we initialize it to a value of null. So that's this data structure here. But everything should start at null, and we will update the value for each key as we go. All right, so it's mainly the setup that takes the most time to explain. Then we just loop as long as there's anything in the priority queue. So as long as there's something to visit, we're going to dequeue a vertex from the priority queue. So that means picking the smallest distance from A. What are we going to start with? Let's say D, because it has a value of 2, and everything else has a value of 4 or 6 or 10 or something. So we start with that, and then the first thing we do is we check, is this the vertex I'm trying to get to? Have I hit the end? And if that's the case, then we're done. Otherwise, we loop through each of its neighbors. So we'd look at all the neighbors for D, and we calculate the distance to that vertex from the starting vertex. And then if that new distance, that sum, is less than what we're currently storing, we update the distances object with a new lower distance. So this is all what we did in the last video, or 2 videos ago, walking through. We update the distance, we update the previous object to now reflect where we came from, and then we enqueue the same vertex with a new total distance from the start node. And that's it, we keep going over and over. So for example, here we'd pick the smallest value using the priority queue. Currently it would have D, E, and F in there because we've done A, C, and B. So we dequeue, which would give us D because it's the smallest with a value of 4. So then we're going to look at D's neighbors. There's 2, E and F. And we start looking at E. Sum that together, it gives us 7. That's actually not less than what we currently have. So we don't do anything. But then we move on to F, the next neighbor of D. So that gives us 5. And if you look at what we stored right now, it's 6. So 5, the new total, is definitely less than 6. So we update it here. Then we come to previous and we say, all right, the new shortest way to get to F is not from C anymore. It's actually to go through D. So we just put D right there. And then after that, we want to enqueue F with the new value of 5 so that it's, updated in our priority queue, and we know next time we're going to pick 5 first because it's the new smallest value. All right, so let's give this a shot. And if you want to, of course, try and implement it, but definitely not something you have to do. It's a little more complicated. If you want to, though, the pseudocode should get you there. Otherwise, in the next video, I'll go ahead and build it.